Welcome for anyone who's watching the live stream or the recorded version of it. We're here today. We're going to look at, what are we looking at today? What are you expecting to see today? Not sure. Just came to class and figured out. Your teacher would know, right? Okay. Lesson 9, or Unit 9, Chapter 9, Unit 2. So because I messed everything up, right? I moved that stuff around. So we're going to look at Chapter 9, which will take us a little bit further into probability and some counting techniques. Now remember, probability is all about counting. So the other thing I've got on the screen, I found a new software where I can actually write on the screen. So I'll be using this. It allows me to save pages also as images. So I'll be taking pictures of those things, the pages as we go. It's also getting recorded as a video. So when you go into Canvas afterwards, you'll see the video of the live stream, at least a link to it, and then pictures of the screens. So sometimes you just want to look through and see, you know, a certain thing. You don't want to necessarily go through the video. Those will be there now. And then we'll also have the videos, and then you also have the other resources in class. So we'll see how this works. I've used it this week in my other classes, and I like it a little bit better than the board, because when I go on the whiteboard, a lot of times the markers run out of ink and you can barely see it in the back, right? So this one, the writing comes out pretty nice and dark, and I can change colors and everything. The only thing is this screen doesn't work, so now I'm going to have to look over there. In fact, actually, those who are watching the live stream, you don't need to see my face anymore, so you'll see I switched that back over. And so just to be able to log attendance, what shall we do for a word of the day? Since you came here, you get a breakfast. Oh, I wish I had some, right? Good. Okay, so we're going to go with breakfast. It'd be nice if we could bring in like a little breakfast bar on the back. Neat way we learn, so, but let's see what we can arrange. Okay. Looks like we've got sound. And so what we'll do, I'm going to take a snapshot of this. Well, actually, I'll just bring in MAT141. Bless you. See, I can just bring the screen right in here. We're going to go into MAT141 just to look at the resources. Maybe. What's going on here? Oh. To switch back and forth between the cursor and the writing part. And incidentally, if you have questions from Chapter 8, once we finish the class presentation, the looking at Chapter 9, I'd be happy to go back in and take a look, and we'll help you with that. When is everything due? When should you have Lesson 8 done?
Today.
Today would be good, or as we're starting into 9, but again, there are no due dates set, so you're not late. But yes, if you had it finished, if you could get 8 finished up, so then you can work on 9. But you'll see 8 and 9 are well connected to each other. Okay, so go to 141, spring. I go to student version. You'll see that welcome screen is now gone, so you don't see it when you log in. We took a look at Chapter 8 last week. There's a video online with what we talked about. Also, if you send me questions, that's what I liked about this software, is I'm actually able to, someone sent me a question from my 121 class, or maybe it was my 91, one of my other classes, and she gave me the problems that she was having problems with. I just worked them out in a little video, posted the video, and gave it back to her, but I also posted it in the class. So so if you run into some questions and send me questions, I think I'll start, if I, I'll start answering maybe some of your questions with videos. So it's like, I'll pull up the question, we'll do it, and then I'll also post those in class, because if you have that question, probably somebody else did. So we'll figure out how to organize it, so there might be like a questions asked, a FAQ place or something that you go for each unit, and you can see maybe somebody's already asked this question, maybe there's a new video on it. So we'll do that. Chapter 9, the things again, there's a textbook. It is this, there's some of the stuff we're going to talk about comes directly out of the textbook. Some of the things in the PowerPoint, I think, come right out of the textbook. So it is designed that you take a look at it. And I guess, sometimes I'll get students that say, well, I don't know how to do this. And then I'll say, well, it was the first example in the textbook. And in fact, sometimes it's exactly the same example. All you had to do is copy from the textbook. So at least take a look. I know sometimes you might miss something. That's okay. So it's, if you flip, you flip. But remember, we do have this textbook, because sometimes I would forget. Yeah. Okay. There's practice problem videos. Now remember, that takes you to another website that has the problems one by one. And what you can do is in the back of the textbook, it's got the actual practice problem, so you can see which one might match up with what you have a question on, and then you could come to one of these videos. This one, I think I started doing the evens, because I thought I was realizing how long it took to do these videos. But they're there. If you had a question on question 30, you can bring it up. And I think if you see, the reason I did the evens, if you take a look at the maybe like 31, it's probably either like 30 or 32. Okay, so these should give you enough of me working out problems to get you through most of the problems in the homework. Okay, but it's not directly tied in. It's not that you can just, from the homework, click on a link that says video and it takes you to these. These are kind of separate. Maybe someday they'll be tied in, but right now it's kind of like research. Have this page open, but again, you don't necessarily know what these questions are talking about, but that's in the textbook. The last part of the textbook has that in there. In fact, why don't I pull that up just to get you looking? So here's, all the stuff. You'll see some of this stuff in here that I need to highlight. And then if we go all the way to the end, you'll see these things. These are the practice problems. Practice problems. So these are the ones I worked most of the evens, if not all of them. And I tried to make sure I worked at least one sample of each kind. So you could say, you could read 4, and if that was one that was like the one you were having problems with in the homework, hey, there's a video on it. Take a look. Maybe it'll help. Okay. Then we've got our class PowerPoint. That's what we're going to go through today. There is also a permutations and combinations calculator. So I put these in fact, let me just click on that. We will use this a little bit later. This is an online resource. It's an online calculator, so it will help you with problems. If you've got a TI-84 calculator, it's got this built in. Some other calculators have it built in, but this is an online application we can use as well. So when we start doing a few problems, I'll pull this up and we'll just use it. In fact, actually, I'm just going to leave it there. Notice I have them opening up in new windows or new tabs, so it's there for your resources. We'll come back to this one and I'll show you how easy some of the problems actually, because we don't have to deal with formulas, we've got a calculator that will do it. We just have to understand a little bit how to do it. Then there's the reading quiz, the homework, and notice how the test is grayed out until I do what? When does a test become ungrayed out?
You get over to 70%.
70% on the homework, the test will open up. And the reason for that is a test is, don't think of it as a real test. It is a test, but it's the homework problems with just a single try at them. So if you do get through 70% of the homework, you've actually already worked the test, and you should see that it goes through pretty smoothly for you. The test questions, remember, you get multiple checks. So if you get it wrong, it's not done. Just ask for another one until you get it right. But use your notes from doing the homework. Again, the goal is that you do the homework, get as much help as you need, but try to do the test on your own as much as possible. Okay. I'm not going to worry about one or two, but if you have help all the way through the test, that also is not good. What we're trying to get you to is at least you've done the homework, you've gotten help on that, but you've gotten where most of the tests you can do on your own with help from your notes. It is open book open. Okay. So I guess I better just start into this, right? Here's the PowerPoint. Word of the day is breakfast. Okay, so there'll be a little attendance quiz. You guys finding out the attendance quiz is working okay?
Yep.
And you'll only, they're once a week, go in and just multiple choice, choose the word. We'll probably do breakfast, lunch, and dinner, and we'll know it's breakfast. Those who didn't watch the video or are trying to scam us, they might choose lunch or dinner, but it's breakfast. That's the important meal of the day, right? In fact, maybe I'll ask, what's the most important meal of the day? Okay. So, PowerPoint's here, downloaded, so let's go ahead and pull it up. And again, I do stick to the thing that when I pull up resources that I'm going to use in class, I pull them up out of MathAS so that you have access to it all. So, I didn't used to do that, and sometimes I'd forget to update things, and so I was using something that you didn't have access to, and that's not fair. And it's not helpful. So, but this should do it. Okay, so here's our PowerPoint. We're going to go to slideshow, and let me set it up. Let's do it in a window. So we'll just go through here. Combinations or combining probabilities. So this is going to be probabilities of more than one thing. So in A, we were dealing primarily with, I roll a dice, what do I get? Or I roll it 5 times, what's the probability of something happening? Or I pick 2 cards. These are going to be multiple probabilities. There's going to be some and probabilities. What's the probability of it raining and having lightning? What's the probability of it raining or lightning? So we've got those 2. So there's the and probabilities and the or probabilities. And we'll discuss exactly what they mean. But it's a little bit different than how we use the words in English. And I forget which one are which, but one's inclusive and one's exclusive. And it's a little bit backwards, again, how we would do it in English. So we'll just kind of work through that. Okay. The other thing is we're going to do a lot of problems, or some problems at least, that deal with a deck of cards. This is in the textbook as well, but if you're not familiar with the deck of cards, here they are. You might need to look at these when you do the counting ones, because it's all about counting. So let's just do a little bit. Usually we don't use the jokers when they're doing probabilities, so these ones at the bottom are not counted. But what they'll do is they'll ask like face cards. Face cards are just these 3 here, Jack, Queen, King. And notice there are 12 of them, 3 times 4, in a deck of cards. The ace is not a face card. Oftentimes it gets counted as a high card, but it's not a face card. Okay, so I've had a few students, they counted the ace as a face card, and of course then your probabilities aren't going to match the answers, but so we go through that. There's 2 sets of red cards, there's 2 sets of black cards, there's diamonds, hearts, spades are down here, and clubs are up there. Okay? So again, we're talking about counting. A lot of times you just need to see what you're counting. So here we get right off the bat an and probability. Doing this and that. This is the inclusive kind of, both, when we say and, both things have to happen. Okay? So, and there's 2 different types of probability with and. One is independent events, so A and B happening. So like rolling a 2 and then drawing an ace of diamonds. So those would be independent, right? When I roll a dice, that's not going to affect what happens with the deck of cards. I choose a deck of cards, it doesn't affect what happens with rolling a dice. They're 2 completely independent events. And in probability, that's an important concept to have. And we'll talk about what's not independent, and it'll kind of make a little bit better sense. But when they're independent, all we have to do is find the probability of each of them and then multiply it. Okay? So this is the multiplication principle. with independent events, it's real simple. Find the probability of each of them, multiply them, and that's the new probability of both of those things happening. Okay. So it's 1/6. There's a 1/2 out of 6 in rolling a die, and then of getting an ace of diamonds. There's only one ace of diamonds in a whole deck of cards, so that's a 1 out of 52 chance of that happening. We multiply the two, multiplying straight across, and we end up with 1 out of 312. Does that seem to make sense? Seem to. Let's go. Okay. Multiplying straight across, we get 1 out of 312. Dependent events. Okay. This is where the first event happening actually changes the probability of the second event happening. It's going to make an effect on it. There's going to be a difference. And so mathematically we get this equation. It's the probability of the first thing happening, because that's, once it happens, and then basically it's the probability of the second thing happening, assuming that the first thing happened. Okay, and we'll explain. It's a little easier to deal with than what they're talking about, or where you see the formula doing here. But let's talk about what happens. So we're going to draw a queen. That's the first thing. That's A. And then the second thing is to draw a 5. And we're not going to replace the first card. So what happens when we draw a queen out of a deck of cards? What does the deck of cards now look like? It only has 51 in it, because it's had the queen taken out. Now, if we didn't get the queen, then this thing doesn't happen at all, right? The queen had to have happened. So getting a queen is going to, what kind of a probability are we going to have to get a queen? How many queens are in a deck of cards?
4.
Good. There's 4 queens out of 52. So that's going to be the probability of A. Now, the probability of B given A, so that we already drew a queen out, what is going to be our probability of getting 5 in the new deck that's missing a queen? There's 4 5s.
So 4 out of 51.
4 out of 51. It's just like that. So it's really, it's like, oh, that makes sense, hopefully. If you think of it as just counting, it makes sense, right? And then we just multiply those two, and we'll have our answer. And I'll show you that switch back to here. Click in, and exactly 4 out of 52 times 4 out of 51. Do the multiplying, and then they reduce it. This is one of the reasons, though, I like to deal with probabilities as decimals, because reducing fractions can kind of just get tedious, and it's not real meaningful, because I don't really understand what 4 over 663. I know it's a very small number, but if you give me the decimal, I'll even understand it better, or percentage. But they pass over this a lot. But if you look at the way I do the practice problems, I turn every fraction into a decimal, every decimal into a percent. Okay, and I think that's good practice. Okay, so far so good. Any questions? Take a picture of our first page, and you'll notice, oops, oh, here's my, I'm just going to call it page 1. There we go. And then down here now you should see this is page 1 out of 1. I'm going to ask for a new page, and all the writing's going to disappear. And now this is page 2, but don't worry, if you had questions, we could always go back, and I can go back and forth now. So I think that's what I'm liking about this software. It kind of records everything as we go. Okay. So now, the other big aspect of today with combining events is OR probabilities. Now, an OR is really, we're looking for one thing to happen, but we're accepting more than one thing. I want either rain or lightning. One of those two things. If I get lightning, it happens. If I get rain, it happens. If I get them both, then that counts as happening. I fulfilled what I was looking for. Okay. So with OR probabilities, we don't worry about independent or dependent. What we worry about is how we count things, whether they're overlapping or non-overlapping. Now, what does overlapping mean? It's easier to talk about overlapping than understanding non-overlapping. Overlapping is when you have an event that is basically in both groups. Okay, so this is an example. You can see this probably one event is drawing a queen, and the other event is drawing a clubs. And you can see the queen of clubs has both characteristics. So the problem is we would count it twice if we're counting probabilities, or we might likely. So one way of approaching this is to count each of these, the probability of getting a queen, the probability of getting a club, and then subtracting off the card we counted twice. So you're going to see that formula. When we have non-overlapping events, it means they can't happen together. So it's like flipping a coin. You're going to get either a heads or a tails, but notice there's no middle ground. You can't get something that's half a head and half a tail. Unless you're doing it in the sand, right? Then maybe it lands on its side. I don't know, but then usually you wouldn't count that. So non-overlapping events, what's going to happen, so look at this, whenever we have something that's an OR probability, we're going to add. Not multiply, add. So that's the difference between AND and OR. AND means multiply. OR means add, because we're adding on. And OR is the inclusive OR. Because usually we ask, like, do you want a hamburger or do you want a salad? And if I say or, you can't, I'm implying you can't have both, right? But in math, the or is both is included in it. You can say, yeah, I want the hamburger and the salad. But see, that's the word, when we use and, it's exclusive. In math, when we use or, it is inclusive. So that's probably the hardest part of this, is the way we use the English words in everyday life is different than how it gets used in math. Sometimes, okay, we can use it both ways. Or, though, is going to be the inclusive or. It's either or both, okay? And when you have the or, you're going to be adding probabilities together, okay? So the probability of getting of the heads or a tail, right? 1/2 plus 1/2. So when you flip a coin, 2 over 2, you have a 100% of getting either a heads or a tail. And did you have a brother or sister who pulled this on you when you were young? Heads I win, tails you lose. Right? Did you think about that? Heads I win, tails you lose. So they always won, right? My sister did that to me, and I didn't catch on for a while. I go, why does she always win? And when she doesn't win, I lose. So then I finally figured out a few years later, when I lose, she's winning. So she had me. Yeah, she had a 100% chance of winning. But she taught me, right? Okay, so those things happen. Overlapping events. So what we're going to see here, and again, the next slide I'll show it. How many queens are in the deck of cards? 4 out of 52. How many clubs are in a deck of cards? There's 4 suits out of 52. One math fact you're going to need to know with a deck of cards, 52 divided by 4 is 13. That's why there's 13 cards in a deck of cards, or in a suit, because there's 4 suits. 52 divided by 4 is 13. So those facts will come back and forth. 4 suits, 13 cards in each suit, 52. 52 is divisible by 13. It's one of those facts that you probably just don't pull out of your head because you didn't memorize it. But if you're going to play cards, those are good ones to have. Those are good math facts, okay? So then we could say that we're going to have 13 clubs out of 52. But then looking at this picture, what did we do with the queen of clubs? We counted her twice. We counted her in the first fraction. We counted her in the second fraction. So what should we do? Subtract her once so that we're only counting, because it's only one card, even though it has the two possibilities, or two things. The nice thing is keep it as 52s. Don't reduce them, because now we've got common denominators. 4 plus 13 minus 1, that looks like 16. 52. And the thing is that's going to reduce. You might not have seen it, but 4 goes into both of those. 4 goes into 16 4 times. 4 goes into 52 13 times. And I think there's a similar question to that. Does that make sense with the OR probabilities? So we just look for overlapping. And how do we know when we have overlapping? We have to look. It's one of those things. You have to look. So we would have to look at the deck of cards and see, hey, a queen of clubs is both a club and a queen. There's an overlapping event. It's not always obvious, but we have to think our way through it and think, could it happen? And if you take a full-blown probability class, these are the kind of things that really get at you, because you forget, you really have to study what you're talking about. So that's the good side of this mathematics. It's not so abstract. It really is concrete, but you have to be looking at what you're talking about. You have to really know it. Okay, so here, questions. How are we doing so far? So, let me back. Previous. Let me take a picture of this, because then that's for a new page, and we'll just click through this next one. Non-overlapping events. So this is where they're going to calculate what we just did. Probability of it. Oh, they changed it on us. Sorry. Sometimes you need to read, right? I thought it was the heads and tails things. Suppose you roll a single die. What is the probability of rolling either a 2 or a 3? Okay. Is there any overlap between a 2 and a 3 on a dice? No, it's not. You're either going to get the 2 up, or you're going to get the 3 up, or something else, but there is no overlap. So simply you add up together. You win if you got a 2, you win if you got a 3. So that's a 2/6 probability, which reduces down to 1/3. So no overlapping, just add them when it's an OR. When there's overlapping, this is the one we talked about. It's a probability in a standard shuffle deck of cards. You draw a queen or a club. And again, this is what we work through. The queen is 4 out of 52. Clubs are 13 out of 52. Subtract off the queen club, and you've got 4 out of 13. Question?
Yeah, so on slide 4,
Yes.
you had overlapping and then the equation, and it said P times A and B.
Ooh,
Aren't we working on OR?
we are. Let's see. Which one was that?
Back
Oh.
one more.
Back one more. Or
Overlapping events, yeah. And then P times A and down one.
wait. Oh, I see. Oh, no, that's correct. That's the probability of A and B happening at the same time.
Okay.
So, and that will only happen if it's an overlapping, and so that's referring to the queen of clubs, which is both a queen and a club at the same time.
Okay.
So good catch, though. So even with the OR probability, when we have overlapping, part of the OR probability is an AND probability.
Okay.
And that's the part we have to subtract, because that gets counted twice.
Okay.
Even
So
though it's a C.
subtract it and then you multiply?
No, we don't, sorry.
Because it says minus the probability of A and B.
Right.
Okay.
So here's you're right. In a more advanced probability class, we could be able to calculate that. We would calculate that with a multiplication problem. But in this case, we can address it with just a counting problem. We can just say, oh, there's only one of them.
Okay.
Yeah, good. See, you're the first one to catch that in years. And I've never caught it. But there is an and probability. And I remember now, because remember I took graduate level probability, and it's the same concepts, but then you get to more and more abstract stuff, and you have to follow these formulas. That's where the formulas come in. But in the beginning, with the concrete stuff, we don't really need to use the formula so much. And one thing you could do is you could say, well, there were 4 queens, and then when you get to count the clubs, you say, well, I've already counted one, so I'll only count 12 of them that I haven't counted. So that's another way, is you don't necessarily need to do the subtraction. I mean, on the paper, you could just sort of do it in your head that, hey, we've already counted, let's not count it twice, and then I'm okay. So there's a couple different options, but this one is helpful for when we get to abstract, complicated stuff, which we won't. We don't do that in this class, fortunately. Okay, good. So this is the one. There's the queen, the clubs, and then we physically count this that there was 1 in the overlap, so we subtract it off, giving us 16 out of 52, not 17 out of 52. 17 out of 52 was counting that queen of clubs twice. Okay, and that's pretty much it for and probabilities and or probabilities. Questions? Okay, and we'll should get to a chance where we'll work a few problems. We may have addressed this slightly, but in here we do it a little bit more directly. There's this rule called when they ask for at least 1 of something. So that means, like in this case, we talked about this in chapter 8. What's the probability of having a family of 4 children, having either all girls, all boys, 2 girls and 2 boys, and so forth. So this comes directly out of lesson 8. And what we did is the question is now assume equal chance of having boy or girl. What is the probability of at least 1 girl in a family of 4? So at least 1 girl. Well, here's 1 girl and 3 boys, so that would work. Here's 2 girls and 2 boys, that would work. Here's 3 girls and 1 boy, that has at least 1 girl. And here's all 4 girls, so that would work. Now, if you would take this sort of in the forward thinking of what they said, we'd have to calculate all these probabilities and add them all together. But what's another way we could do this? And usually this is the easier way. There's only one thing that doesn't fit our probability. So if we calculate this, which ends up being 1 out of 16, right? Because there's 16 total choices. But remember, that's what we don't want. We don't want a family without a girl. So you subtract that from 100%, which is 1. And 1 can be written as 16 out of 16. So you're going to see it's 15 out of 16. Now in the cases we're going to look at, we could have also counted that there's 15 out of 16 families that have at least 1 girl. But this way of counting is a little easier, again, for probably more advanced counting things. Let's take this one. It's going to work it all out for us. So now the thing is that I didn't like how this book did it. It then takes 1/2 chance to the 4th, but how did that get calculated? I don't know. Anyway, it's this one. It's just counting. Okay. So again, in this class, it's not going to be as critical, but I remember taking tests, and I would work on this problem. I said, wow, this question is so long. Why did he put this on the test? And then at the end, I'd say, oh, it's an it was an easy question. I just needed to calculate the at least one and subtract from one. I was doing all the other counting that I didn't need to do if I would have paid attention that they said at least one. Okay, so look for that. It just makes the calculation a little easier. You're finding what you don't want. Sometimes it's easier to find what we don't want and subtract it from one than to find what we do want. Because, does that make sense? Okay. Good. Now we're into counting and probability. So basically, we finished the first section. Now we're going to focus more on counting. Yes.
In that section, they had 9.3. It was it was a you try problem.
Okay.
And it said, okay, so it considers that you roll 2 die. What is the probability that the sum of the 2 die is odd or one of the die is a 1?
Okay.
And since 1 is odd, I don't know.
Okay. Oh, good. 1 is odd, so what do we have? We have an overlap.
An overlap.
Good. So let me pull that up, and we'll take, what page was that on?
It's on page 196.
Oh, your pages are different than my pages.
Oh.
But we should be able to, but it was 9.3, right?
Yes, 9.3.
22. 9.5. Okay. Here would be 9.4. And it was example what? Oh, so you tried.
Yeah, you try. It's
here.
right under there's like a...
Okay, here it is, yeah. Consider again we roll 2 die. What is the probability that the sum of the 2 die is odd or one of the die is 1? Now 1 itself is not, it doesn't necessarily mean, because we rolled a 1 does not mean we end up with an odd number. We could roll 2 1s and then that the sum is even actually. Okay, so what we need to do here is we need to count, and so we're going to remember that we get either an odd number or the die is a 1.
In the example before that, they've got, yeah, so you don't need it.
So we go here, that's good. So this is what we want to look at. Make it a little bit. So, anything with a 1 would count. So in this column, these all have a 1, correct? In this top row, these also all have a 1. Okay, so we could calculate the probability that one of the dice is a 1. It doesn't matter if it's the first or second, it's how many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I was careful, I was counting them specifically, so I didn't count this one twice because it's got both of them, right?
Oh, okay.
So if you just careful how you count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 out of 36 total possibilities that have a 1. Okay. And then we can come back and what's the probability of getting an odd? And again, we kind of have 2 ways to do this, and since we're just looking at the numbers right now, we don't have to worry about counting the odd ones that are in the ones we've already highlighted here. Notice this top row or the bottom one, if we just ignore those, we don't worry about whether they're even or odd. What we're going to do now, in fact, let's change colors. Let's go for red. I could come through as 2 plus 2 is not, so anything, let's see, 2 plus 3, that's 5. So that's odd. This is even. This is odd. That's even. 3 and 6 is 9. That's odd. 3 and 5 is 8. 3 and 4, this is going to be odd. So I'm just going through, and 3 and 3 is 6, so that's not odd. 3 and 2 is, basically, a sum of numbers. If one's odd and one's even, it'll be odd. If they're both odd, it'll be even, and if it's got both even, it'll be even. So I'm just looking for pairs that have an even and an odd. That sum will be odd. It's an even and an odd, because they're both even. Even and an odd. Odd and odd is going to be even. So I'm just counting, and hopefully I'm doing it. So that's going to be 8. That's not. That's even. This would be an odd number. That's even. This would be an odd number. Now I just need to count how many I've done. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 out of 36 that are odd. And notice I didn't go in, I didn't worry about the overlap because I didn't count anything twice. Now, to use the formula, we would have actually gone into the ones that we had previously counted and figured out what was even and odd, and then counted the overlap. But the problems we're going to have are going to be simplistic enough that we'll be physically able to see what we're counting and just count them. Okay? So what I would do at this time is I just add these two together without looking at the overlap, so I don't have to subtract everything. I was carefully counting, and I didn't count anything twice. Yeah, exactly. So 11 plus 12 is 23.
Yeah.
Right? 23 out of 36. 23 is a prime number, so that's not going to reduce. And
All right,
good.
thank you.
So
I think I counted the 1 twice.
yes.
And then counted all again up here, and then tried to subtract it, and I just
Right.
Okay.
It's that's really hard for me. It's hard to try to, if I count it that way, if I really try to count everything and then try to figure out what got counted twice,
Yeah.
it's better to me to just, if I can just carefully count things and not count anything twice. If I've counted it, I get it out of the way.
Okay. That's what I'll do.
And we can do that here. Again, if you go to graduate probability, which maybe some of you will, but I recommend not. No. Then you have to worry about it because it gets so complicated. But yeah, if you were going to work for an insurance company, that like an actuarial, they get into things like that. So it's good to understand that. But for the simple things, just count carefully.
Okay.
Make sense? Okay. Good. So we've got that example in there. This is what? This is page 4. Okay. Get a new one. And what do I have? So we'll get back to the PowerPoint here. Counting and probability. So this part is primarily going to be on ways to count when we do have a large number of things. Okay. And primarily it's going to be using something called the multiplication principle. Okay. And it kind of comes out here is we're putting things in order, or we've got a list of numbers, a list of words, and we're trying to count how many different things can I do, like with a license plate. So for a license plate here in California, evidently in this particular one, there's 1, 2, 3, 4, 5, 6, 7. So there's 7 numbers in a license plate, and so you could just put a list of 7. And we're always going to be multiplying with this so the counting principles is always about multiplying. And I'll show you also there's a permutation, there's some formulas that they use, and again, those formulas break down into a calculator function, and I'll show you how the calculator function works. So what happens is, what we do is we think, oh, for this first slot on my license plate, how many choices do I have for digits? Well, if I 10, because I can also use 0, 1 through 9 plus a 0. Now sometimes you can't have a leading 0 or something. You look at the rules, but this time they just say any digit. Second one, I can reuse them. Now if you couldn't reuse them, you'd only have 9, but in this case we still have 10. And we have 10 for the next, 10 for the next. We have 10 for each of these. So it's really just 10 times 10 times 10, 7 times. So you'll see a shortcut for this is when we can repeat we have 10 things, 10 to the 7th power. Okay, and that's going to be a 1 followed by 7 zeros when you multiply it out, which is a lot. It's like 10 million. So 1 with 7 zeros. 1, 2, 3, 4, 5, 6, 7. We come back and put in our thing. That's 10 million different license plates, which sounds like a lot, but if you've been to California, what do you know about California? There's more than 10,000 people. There's more than 10,000 cars probably too, all just in LA, right? Oh, okay. Anyone from LA? No? I've been through there, drive through there a few times, and always glad I don't live there, but okay. So, but the principle is just you're counting how many slots you have, and then you're going to be multiplying. And basically, we're going to look at whether we can reuse things. If we can't, then the second slot there would only be 9 different things because we used something. 8, 7, 6, 5, 4, 3. Okay, so that's how that's going to work. So here it is. There's a formula here, and I'll explain that formula probably later, or not, because I'm going to show you the way we can do it without even using this formula. Okay, we're going to think through this, and we're going to just use our slots and our multiplication. We're going to see that it works. I'll show you how the formula works, and you'll see it's really the same thing. So why use this funky formula when I can do it a lot easier, right? So we've got this, this is a question, and I'll just look at the pictures. I like things with pictures because they're easier to explain. We've got a dive team, and we are going to have to choose, evidently we've got 10 girls on our team, and we're going to choose 4 divers to dive for the competition. So how many different dive or lineups could we have? And has anyone in here done diving before, or competitive diving, or let's stick with red? No competitive divers? Any competitive swimmers? Any track people? Any baseball or softball people? You've never played baseball or softball? At least played it, no? You gotta have played softball at least once, right? Okay, softball. So the order, okay, because actually that's a little different, but in diving, how do you score points? How many people have at least seen something like a diving? You've probably seen at least a commercial that had diving, right? How does they earn points for diving?
Form, splash.
Okay, but and who gives them the points?
Judge.
Judges. And they're supposed to be objective, right? But it's not. My dad used to do competitive roller skating and ice skating, and he says there's this your position, whether you go first or last, or it's not good, because the first people, they're real conservative, they're saving the points. By the end, they've already given away the good points. He says you always want to go kind of in the middle. So the order does matter as far as what you're going to get as points. So how many different permutations, how many different lineups of divers could we have? Well, we're going to have a first diver, a second diver, a third, and a fourth. And that's going to be our team. How many choices, how many different girls could go first if we have 10 on our team? 10. So once she does, let's say it's Susie. We have Susie be the first diver. Now how many choices do we have for the second one? 9, because Susie's can't dive again. She's already dived. So we have Brenda. And now that Brenda's been chosen, how many do we have to choose from? 8. And we have, what's another good girl's name? Amanda, thank you. So Amanda dives. And then we only have one more slot, and how many girls can we choose? 7, right? There's 7 girls left, and we choose our 7th dive. So that's the total number of divers, so there was 10 from the first, 9, 8, 7. And it's like this pattern. We had 10 girls to choose, and then we've got 9 girls to choose. So this gives a tree diagram thing. So if you take 10 times 9 times 8 times 7, what do we get? Has anyone got a calculator out? I'll just do it in my head. Or actually, I'll just cheat and look at the answer, but okay. You thought I was really amazing, right? Okay, I fooled you that way, but not too much. Yeah, so if you multiply it out, you get 5,040 different actual lineups that you could come up with because you've got your 10 teammates that you could choose from, the coach could choose from. And let me explain what's going on here, because that's what the formula did. Does anyone know what this is? What's this called?
Factorial?
A factorial. And you probably said, that's something I see in English. It's when you make an exclamation, right? So 10 factorial, though, what that means is it's a mathematical way. It just means you start with 10 and then you work your way down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and you're multiplying. Okay. So the way this formula works, the top is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Off the screen there. The bottom is this thing since we're choosing 4 out of the 10, you did 10 minus 4, which is going to be a 6 factorial, which they show down here, which is 6 times 5 times 4 times 3 times 2 times 1. What happens to the back end of this? 6 divided by 6 is 1. 5 divided by 5 is 1. 4 divided by 4 is 1. 3 divided by 3 is 1. 2. It all cancels out back here, and what are we left with? 10 times 9 times 8 times 7. So you could do it the mathematical way with this formula. That's a lot of work. And then you got this canceling out, or you could just think through the problem. I've got 4 slots, 10 girls. It's going to be 10, 9, 8, 7. And these will be all this is how all the problems will work when the order of our selection matters. Okay, so that's in our counting problems, we have 2 kinds of counting problems. One is order is important, and one order is not important. And we'll talk about the difference. But in this case, with lineups, order is important. There is a first, second, third, and fourth. We're choosing maybe a representative government, and we have someone be a president, a vice president, a secretary, treasurer. Since they're getting titles, the order we choose them in is important, because the president has a certain amount of job title, as the secretary has a different job title. Okay, so we're going to look at some cases when order is not important. The formula basically is the same thing with a little bit more complication, and then we're also going to, as we start calculating, I'm going to show you there's a calculator where we actually can put these in and not even have to worry about either one of them. Okay, so there's a couple approaches. When order is important, I'm just going to tell you right now, this little process we went through here, just thinking our way through the problem, is actually the easier way to do it. We're counting it that way. But when we get to the combinations, when order is not important, it's actually going to be easier to use the formula in the form of the calculator. Okay. And we're almost done. Let's see, how many we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, shoot. We don't have enough in here for me to make any money today. Or to even get a free lunch or anything, but I'll show you the problem. Okay, so I mean, this is the one we just sort of went through, or it's similar. International track event has 8 athletes participating in 3 gold for 3 medals, so they're going to race, and that'll be a gold, silver, or bronze. Is order important? You betcha. You get the gold, you're on the Wheaties box, right? You got all these, you make millions of dollars. You got the bronze, and nobody will even remember who you are. And even though you were the 3rd, right, You get about as much memory as the guy who was last. But notice what happens. There are 8 people running. We're choosing 3 of them for medals. Order is important. So they come up with this calculation. And again, what I would, as I would do this, I would just focus on, there's 8 people that could get first place. Since one is, and then there's 7 left, and then there's 6 left. I would just do this calculation right here. And that's what gives us 336. 336 different possible winning combinations, or winning permutations, we should say. Permutation is the correct word to use when order is important. Okay? So far, so good. And again, there's I've worked several of these type examples out as well. We'll see how that relates to probability as we move forward. Clear that. Okay. Now this is what happens when order is not important. Order doesn't matter. So this is like I'm making a selection for a committee, and I want to choose out of these out of the students available today. I think we had 12. I want to take 4 of you and make a committee, and you guys decide what we're going to talk about next class. Okay. If it's a committee, you're all equal. There's no positioning. The order that I choose you in isn't important. Same thing happens with lotteries. If you're into like Powerball or such, the order that you chose the numbers in doesn't matter. You don't have to get, it's just that your numbers were chosen, but the order that they were chosen in doesn't matter. Okay, so there are a lot of things in the world where order doesn't matter. There's a lot of things in the world where order does matter. We have to decide which one is which. What you'll see here is when order doesn't matter, what has effectively happened is, again, as far as the formula part, this part is order is important, and then what you're doing is you're dividing out by the number of ways you could organize it or arrange it. Okay, so that's the mathematics of it. So basically you could calculate the same way we've been calculating, but then we're going to divide out however many factorial we're talking about. Okay, so we'll look at an example of this, and then I'll also show you the calculator, which is actually, when we get to this part, the calculator is a lot easier to work with. In fact, for some of the problems we're going to work with, it's like you have to use the calculator, otherwise you're not going to quite get the right answer. Or it becomes harder to get the right answer. Okay, so we're going to choose a committee of 3 people are needed out of 8 possible candidates. There's not any distinction between committee members. How many possible committees would there be? Okay, so I'll show you how I sort of think of this one, and then we will have the system work through the way it thinks of it. Okay, so there's going to be 3 choices, right? We're going to choose these 3 people. How many people do I have to choose for my first committee member? Good. 8. Choose Fred. So then how many do I have to choose for a second committee member? 7. Choose Louise. And the third committee member? 6. But I've been told that the order that I chose it in wasn't important. It doesn't that the first person has more authority or anything. They're all equal. So it doesn't really matter if it's Fred, Louise, Barney, or Barney, Fred, Louise, or Louise, Barney, Fred. The ordering doesn't matter. So what I have to do is I divide out, because this number that it's going to give us, 8 times 7 is 56, times 6 is going to be a big, I think it's 336, if I remember right from the last page. You got a calculator to be sure. But what we're going to do is that's if order was important. There's actually fewer committees. What we're going to do is we're going to divide out, since we chose 3, it's going to be 3 times 2 times 1. If we would have chose 4, it would be 4 times 3 times 2 times 1. Okay, it's 3 factorial. So we're going to divide out 3 times 2 times 1, that's 6. And what you'll see is if you do the division a little bit sooner, 3 times 2 is 6. It makes actually the calculations much easier. Or you could take 336 divided by 6 and get 56. Okay, either way, there's actually only 56 different committees that I could choose out of 8 people, because order's not important. If order was important, there'd be 336 different executive boards if I gave a president, vice president, treasurer, something like that. Okay, does that make some sense? Okay. What I want to do at this point, though, is, let me go to this. I want to show you how we could use, better backspace. Let's go back to this. Let me save this. Okay, so here's a permutation combination calculator. The nice thing is it will calculate both for you, and then you choose whether order is important or not. So what you have to do is number of sample points in set n. So this is the number that we're choosing from. We were choosing from 8 people, right? We had 8 people in our group that we could choose from. Now the number of sample points are, how many are we going to put in our committee? We're going to choose 3 of them. So this is the problem we just did. We put in 3. So out of 8 people, we're going to choose 3. We know order is not important, but I think this calculator, actually it's already calculated without us touching the button. If you want, you could hit the calculate. That feels good. It says if order is important, there's 336. If order is not important, it's 56. We just did that, didn't we? This just did it all for us. It's all behind the scenes, but you're going to see this calculator is going to be a nice little thing as we get larger numbers and such. So it allows us to get either the permutation or the combination. All we have to know is how many are we choosing from. You know, so if we're randomly choosing a letter of the alphabet, how many letters are there in our alphabet? A, B, C, D, E, F, G, 26. Good. So in the English alphabet, there's 26. We're glad in the Thai alphabet, I think there's like 42 letters. Chinese, they don't have letters, they have characters, and what? There's over like 5,000 or something. Anyone study Chinese? No? Anyway, it's a lot. But we only have 26, so again, so you'll see there'll be questions about that. How many different word possibilities are there? 26 is going to come up. Okay? Does the calculator look not too intimidating? You just, N always has to be bigger than R. Someone ran across this, right? You can't choose 5 things if you only have 4 things. You can't take 5 things out of 4. If you had 5, you could choose 4 of them, but not the other way around. So N is always going to be bigger, the number in the sample, and then the ones we're taking is going to be less. Okay. I think we're just about done. And again, they worked it all out with the formula, and notice they also got 56. So it's kind of got the stuff we worked through. But again, what I want you to see is you could kind of think your way through this by just thinking slots of people, and we're choosing them. Okay. And then now this is where we get to have some fun. This is a question that seems very hard to solve. What would you think the probability of 2 of us in this room having the same birthday? Not the birthday, not year, but just day of the year that we were both born on the same year, day of the year. Would you think it would be very likely? I see a little shaking head. And we're going to see 25, because it's if we had everybody in class today, which I think we've got like 30 people registered, I would be asking for some bets right now, and I would be in a pretty good shape. I'll bet you we would get somebody with a match. And every time I've had a class of about 25 or more, I've always had 2 people in that class, almost always. I think there was one when it didn't happen, that had birthdays at the same day. What we're going to do is, this problem is a little complicated, but what you really do is you start thinking in terms of, this is like that at least one. So you start thinking, let's calculate if the probability of none of us having a match, okay, because that's actually easier. And so the way you go through that, the symbols on this thing's all messed up and it's not worth repeating. But the first person has a day they could be born on, so how many days does the next person have to be born on? 365 days in a year. So the next person only has 364 days that they could be born on. And we don't have to count the first person, because the first person is 365 out of 365, that's 1. The second person, if they're not going to match, they can only have 364 days they could be born on. And then once they have a day, there's only 363 days left for the next person to be born on that isn't a match. And you go through and you do all the multiplication. And it depends on how many students. But if you had 25 students, it's a 0.431, which is a 43% chance of not matching. So this is your math day. What's the probability of getting a match? If it's 43% chance of no match, 57, better than half. 25 is a good place to be. Okay, it's still not, I mean, it's a little bit better than 50-50, but but the thing is if you start getting more people, okay, so they did it, yeah, so you're right on, about 57%. If we get more people, so this is with 10 people, this is about where we're at, and what's that? And this is 11% of a match, so they did the math for us. So that's why I'm not going to bet today, because I only have an 11% chance of making. The only bet I would make is that there's not a match, but then there probably is going to be one, just to show me wrong. 15 people, if you're in a room with 15 people, there's about a 25% chance of a match. That's still pretty good. But again, you do this as a party favor type thing. If you're in you're in a group of 30 people, there's almost a 71% chance that 2 of you in that group have a match. That's the thing. And if you get into something like there's 45 people in a room, again, most people would think, well, there's 365 days in the year, there's 45 of us. It's kind of not likely that we're all going to have, that 2 of us would match the same birthday. But this shows differently that there's actually a 94% chance of getting a match if you have 45 people in a room. And so, get stuck in an elevator or something and say, hey guys, I bet you one of us has the same birthday. And I'll say no. If you got 45, you're just going to happen. You're going to do it. So again, we go through this because sometimes things that on the surface might not seem very likely actually are. And the opposite could happen too. Something that might seem to be very likely to happen could, maybe when we did the math, prove to be not so likely. Okay, and that's, yes?
So when we do this bet, and so that usually there's always a match, is that date usually the same too?
Well, not the date, because then we'd all the age. Unless you were in like a high school class and they're all 18-year-olds, then you're probably more likely to do this. But like this, I wouldn't expect the date to be the same. But I was born on April 3rd. Anyone else on April 3rd? I did this once and someone said, yeah. So no one else on April 3rd. Now, yeah, so we don't use the year. Let's just see it. So I was April 3rd. October 20? Any October 20s? No.
December 24th.
December 24th.
Lower.
Day before Christmas. That's Christmas Eve, right?
Sounds fun as it sounds.
Yeah. Especially for your mom, right?
March 28th.
March 28th. Any other match? No matches yet?
May 4th.
May 4th? No.
September 13th.
September 13th? No matches yet. See, I'm not expecting one, so
August 4th.
August 4th? No.
November 18th.
November 18th? Still not? Yeah.
January 18th.
January, well, we got the days match, but not the month, so, but that didn't count.
May 27th.
May 27th, not yet.
October 1st.
October 1st, we got a couple Octobers, but we haven't matched the date.
November 23rd.
November 23rd, and that's our last chance. You weren't November 23rd or any of the others.
September 30th.
September. So we were all different. And that's what because we would have only had an 11% chance of matching, so that would have been, you know, major thing to do. But again, if we would have had 30 people in here, we would have had about a 70% chance. And usually, when I go doing that, 2 people have the same birthday. And it's just, you know, sometimes the thing is you meet somebody who has your same birthday, and and especially if you like them or something, you think, oh, this is like the angels have gotten us together or something. But you know, if you were on like riding on a bus and there was 45 people on that bus, you're likely to have the same birthday. I mean, well, it doesn't say that you're likely to match up somebody, but it's not as out there that you actually ended up having the same birthday as someone on that bus. If there was 45 people on there, this is not 45% or 94% chance that you will match somebody, but that there will be a match. But I've seen, you know, and sometimes I run into someone who has my same birthday and say, wow, we must have been meant to be together or something. You know, just get this natural thing, and it has nothing to do with that. That's just that's probability. It's the nature. But sometimes we do it, and then we start hating that person or something. I don't know. I always find that the people I like the best were the people I really didn't like the first time I met them. I don't know. I'm just sort of that kind of thing. But probabilities and stuff, it helps us, you know, with these things that we think are, you know, these strange coincidences that we think something, you know, the heavens are in motion and making this all happen. It's just probability. Okay, sometimes maybe there's more to it. You know, and again, if we would have had a match in here, it's the probability says it wasn't very likely, but it's just as, you know, especially what if we could have had twins in here, right? Wherever they go, they would have a match most of the time. So, and that's pretty much the end of the lesson. I think we go through this. Yeah, that's the end of the slideshow. And those are basically. Won't save this stuff. That gets you a good start, and then these problems will help you with some of the specifics of walking through things, walking through problems, and basically you just come back. You know, the reading quiz, remember, that's a good start for things, but it's not required, but it does give you some extra credit points. I haven't started loading up things in the grade book yet. I probably will do that this weekend because I just, you know, get yourself started. It's all recorded there, and then I'll start tracking things. The other thing is when I start tracking the grade book, you start seeing, if you haven't got it done, you'll start to see zeros. Don't freak out. It's okay to have a 0. It's not that, you know, because I'll get people, I thought we didn't have any due dates, and now I got this 0, because a lot of grade books, if you have a 0, you can't undo it, right? Well, this is just a temporary holder. It just says you don't have it done yet, but I'll do that, and so that as we go, if you could have all these zeros, you can make those all up at some time, but it just says based on the pacing of the class from the syllabus, we covered this and it's gone now. But so don't worry too much. It just kind of gives you a pacing of whether you're on track or not.
Would you mind going in the homework? They do they have a chart. It's about they have pregnant women and things.
Oh, good.
And it would say given. I don't know. It's just confusing for me.
Okay. Do you remember about the number?
It was around.
Yeah, Josh, I thought you were doing one like that, that had the table of numbers.
Maybe it's open to huge floor now.
Yeah, okay. So it was, I remember walking by and seeing it, but I couldn't remember which one it was. So we'll just, like this. Yeah, see, given that they are male.
Okay, so what does that mean?
Okay.
Because I would get confused, when it was the pregnancy one,
Mm-hmm.
or no, speeding cars, and
Yes.
they were red.
Right.
And it would be
So this is actually making it easier than it sounds. So this, so we're given this information. It says this test was given to a group of students. The grades of gender are summarized below. So we got males, females, total, and we've got grades of A, B, C, totals here. So total males is 42. Total number of A's is 22. Okay. So if one student is chosen at random from those who took the test, find the probability that the student got a, it's kind of hard, got a C, so got a C, given they are male. So what that tells us is, as we go to count this, we're just counting. We know that they're male. The given says that we know that they're male. So what's our total number that we're dealing with? 42, not the total number of people. Okay, so when they say given, it means we have information that we know something in advance. So our total number is going to be out of 42, not 76.
And not 22.
And not 22, because that's all the C's, and we know that the C's, that there are only 9 males that got C's, so we have a 9 out of 42 chance of choosing given that they're male. So it's maybe the room is divided into males and females, and we're just going to randomly choose from the male group what's the probability we get someone who got a C, 9 out of 42.
Okay, so the given part is your denominator.
It is.
Okay.
And it's sort of telling you we're only counting in those groups, so we only have to figure, so basically we can ignore all of the table except for this row. Now, if they said given that they had a C, then we would have been working from this row. 22 would have been our total. Then it would have been 9 out of 22. We would have lined up the people by grade and chosen from there. So the given, yeah, it tells you you're working, which row or which column you're working with and what your total is, and then you just pick it out from there.
Okay, thank you.
And again, in more advanced probability, that goes into a formula, and learning to work with that formula becomes important in more advanced classes. And not that they're more advanced, but they're just more specific. We don't go that deep. We stay in the kiddie pool part of probability.
Okay.
But we're learning all the concepts we're learning are the same that you would in the deeper end. It's just that you have less support and it's just more complicated. And but you're picking up the basics that will take you as far as you want to go with probability. Okay, is that helpful? Because yeah, and if you haven't looked at this yet, that's one of the things that comes up is you get these tables of values, and it's really just be careful how you count, and then yeah, try to understand what they're talking about. And this given thing is that basically we have some advanced knowledge. We know we're choosing just from the men.
Okay. Thank you.
And so then we ignore the rest of the table. Good. Save that one too. And this is page, I lost count where we're at, so I think we're like 9. That's good. Okay. Any other questions? Okay. I tried in my other classes, when I'm live streaming, I can pull up YouTube, and if you're on the streaming part, you can actually send messages, but I have a hard time. I get real distracted, so I haven't had that up. So if you've been watching live streams in the past, or those who are, and if you've been sending me messages, it's not that I'm ignoring you. It's just I'm not technologically savvy yet to be picking those up. But I hope to be able to do that, because that's what I'd like to do. Is even if you're not able to be in class, but you have questions, that the live stream will allow you to ask those if you watch during the live stream. And then that makes it more realistic, because as you ask questions, we get real things that you might have, and then it's recorded, and then people who weren't here get to see it. People in the online class are now getting a live performance of what's going on in class, in addition to all the videos that just work through problems. Because I feel there's two different things. You want to see sort of how things work in general, and that's what I try to make in class. And then you want to look at specific problems, and I can just sit and work through problems, and those will be helpful if you have the overview. So that's what the class will always be more about, the overview of things, the concepts, and then the videos will be those. And remember, if you have a particular question, I'm going to start trying to answer back your questions with videos, so that we'll get more and more video, because once it's done, right? And 5 years from now, that same question could get answered with a video, And so I could just click on videos and say, here you go. But I think also, the one student I did send that to, if I would have just sent her worked out on the page, she might have understood, but by walking through with a video, she said it actually helped her find exactly where her errors were. And I was, because it's a little bit richer way of going through things. And with this new software, I'm finding it's pretty easy for me to do. Is just pull up an email. I've got a paper, I'm writing it, I'm recording it as I talk you through the problem, and I send you a link to that, and I can post the video link also in the class, so it could help other people who might have that question. I'm running out of air and things to say, so we all good? Okay, so what happens after this?
They'll have, they have one side left, one side right, so like a positive, pregnant. So is positive your denominator?
Let's take a look at that.
It's question 6 in the reading.
Pregnancy test was given to women a round answer. So positive pregnant. Yeah, the thing after the line is the given.
After the line is the
yeah.
given. Okay.
So on this one, pregnant is the given, and so what we do is we just highlight this row. This is the information we're working with. Real good. So positive is here. So it's going to be 53 out of 62.
I see. Okay.
Yeah. And so each of those, the second one is the given.
Okay. Thank you.
That's a format. In fact, I'll write that here. Okay. And this is what we're looking for. So. Okay, so then what happens after this? I actually stopped the live stream and then restarted it. I'll stop the live stream now. It's office hours, or class goes to, I don't know, what, 11:40 or something, and then I've got office hours. So you're welcome to stay